just note these things. So you can just write in your chat what your kind of level of experience with R is, or whatnot. Then I can kind of tailor this to and kind of go as slow as I need or as quick as I need if people want me to speed up. But today's all about just kind of getting code to run faster through something called vectorization. And then we're also trying to get to functions. I'm not really sure how long it'll take, so I'll get into a little bit of the function part, but functions probably going to be a two-part thing. So I might do it again next week if I don't get too far into functions as well. But we'll start with vectorization. Somewhat familiar, cool. So people somewhat familiar with it. This is also good because then I can get you guys to start putting stuff in chat. So if you have any questions throughout, just let me know, stop me in chat. I'll try my best to answer. I'm no expert, I don't think, in these two subjects necessarily, but I've done quite a bit of R coding, so hopefully I can answer something. I know nothing. Okay, so we got some beginners, so we won't like skip through everything super quick. That's for sure. So I think what I'm going to do is I'm going to throughout we can like measure times of things using a package called microbenchmark. And if you're more experienced with R, you might be more interested in trying to measure things and seeing how long things take. Because in the end, when you're optimizing code, you never really know how long it's going to run. You might know that vectorization is faster than other things, but you will never know for sure if your function is faster than another function unless you try it out and kind of interchange different parts of code. So I'm going to teach you how to kind of, or show you one way to do that using this package microbenchmark. So for anyone who's more familiar with R, it may be more of use to you to try this out yourself while I'm going through. But anyway, if you're following along, again, it's always good to have a second screen if you can, so then you can kind of follow my screen and then write on your screen in RStudio just to follow along. If you're not comfortable with following along, that's okay too. This is all recorded, so it should eventually get on YouTube again. But let's just, I guess we can start off now since we've got kind of some answers here. Thanks everyone for answering. So for everyone new, we're just going to work in a script today, but you can work in R Markdown if you like, if you're more experienced with that. But we'll just go file, new file, R script. Let me know if you can't see my screen, by the way.
Sorry, Kevin, I just have to interrupt.
Yeah.
I was just wondering, the poster says that it's the February 1st. The workshop was on February 1st, but we were saying February 8th.
It's definitely booked in for the 8th, yeah.
Is it 8th?
8th, yeah.
Okay.
So I know.
Double.
Okay, cool. I think we were just debating whether or not we could do it on either, but yeah. All right, so if everyone's got file, new file, R script, we'll begin kind of vectorization. So vectorization is really just I'll explain in a sec what it means, but it basically is we're just using vectors, which are basically a column of data to expedite calculations. And R is really good at using vectors of data and combining them together and doing things with them. So the first thing we'll just want to do is just create a vector of data. So we'll just assign X some numbers. So this is how we assign a sequence of numbers, 1 to 4. And I'll go Command Enter, and you can see if I highlight it and go Command Enter, which is run, it'll shoot down to my console and it'll run 1, 2, 3, 4. You can also just click run here to run it, and it'll take the code from my script to my console. Hopefully this is pretty familiar for most people. And then when we run the whole thing, Command Enter, now we've assigned X the values, and X contains 1, 2, 3, 4. So we've created, X is currently a vector. To check if X is a vector, we could go is X, and it would tell us a few things. And one of them is that it's a vector. So we know that's a vector of data with that. So we're good to go with that. And the cool thing about vectors is we can just take them and do operations to them, like X times 2, and it will times 2 to every single element in that vector really easily. So it's really nice if you've got a ton of data and you have to, maybe there's some scaling factor, you have to change it really quickly. We just do times 2 times whatever scaling factor. We can quickly change it to a new scale or something like that. Similarly, you can do like log of X, other things like that. It'll do it to each of the numbers element wise. So these are really key things that will be really quick. And this would be way easier than, if you remember previously, we talked about for loops. If we ran a for loop and went through this individually by changing like the index, it's going to be so much slower. So vectorization is really good because it's kind of built into R, and it's going to expedite calculations this way. So these are examples of element-wise vectorization. So we're doing like times 2, log of each element of X, and it's just going down the list. So hopefully that kind of makes sense what it's doing. Another cool thing is once we get more complicated, so these are like really simple calculations, but we might go even more complicated. We might have another vector called y, which I'm going to go from 6 to 9 now. And we can just run y, command enter. So we've got this second vector y, and just the same, we can also do element-wise operations across two different vectors. So we can do x plus y, and this runs, and basically what it's doing now, if we just look at the elements of x, the first element of x is 1, the first element of y is 6, sorry. So 1 and 6, we add them together, that's 7. Then it takes the second element of x, which is 2, it's the next one after 1, and then 7, and then we get 2 plus 7 is 9. So it's doing it basically lined up the two vectors and adding them together really easily. So it's doing, already you can see like the level of calculation, like complexity can go up like really fast from here. So we can even do the same thing. We could change this to x times y, just copy this and go x times y. Same thing, it'll now just multiply each element of the vector. So like the last vector element is 4 and 9. 4 times 9 is 36, I believe. I'm terrible at mental math, so just I'm assuming that this computer is correct. So yeah, it looks good to me. So this is how you can be like me and be a modeler in R and know nothing about mathematics because R will do it for you perfectly every time. And as long as you just kind of keep track of where everything is, everything lines up and is okay. So R will save you in that way. Now let's try just doing this exact same thing. Let's do the plus one, but we'll build it using a for loop. Hopefully everyone kind of remembers for loop. If not, I'll just get us started with how to build a for loop. So the first thing we'll want is like an output vector. I'll just call this out. It's often what you call an output vector, or like something that we want like the end result to be inside of. So we want our end result of this for loop. I was going to write that I'm making a for loop. For loop, same thing, but with a for loop. So if we're making an output vector out, we want this to cycle through our elements and add them together. So I'll go like, so did everyone remember what is the first thing a for loop starts off with? Does anyone remember? It starts off with 4. We can give it that, and it'll light up a different color because 4 is like a special word in R, and it means it's reserved for a special function. So you can't override 4 with like a value of 2 or something. It won't like that. And if you do, you'll cause other problems. So I wouldn't recommend it. But the way a for loop starts off is we always got some conditional, and it's going to be in parentheses. And then we've got some kind of thing that we're running in these curly brackets. So this is kind of conditional. So it's like 4. And this is where we're going to put some kind of number that's changing or thing that is changing. And usually for for loops, I don't know why, but coding programming languages, we always use I. So we go for I in, and then we can set some number. So since each of the X and Y have a length or a number of elements of 4, we're going to use I from 1 to 4. So what this is saying is that we want I to be first the value of 1, go through the cycle. Then we want it to be the value of 2, go through the cycle. Then the value of 3, go through the cycle, and then value of 4, go through the cycle. So that's what we're doing with this. So this is a conditional kind of part of the for loop. So this is where we set what I is going to change from. And sorry if you missed the for loop one. I'm just kind of going through it rather quickly, but don't worry, it's not super important. We're just trying to build a for loop so we can compare it against vectorization. And now I'm going to go enter. And now here's where we put in what we want it to do. So for instance, I could go like print I, just to recap. And if I do this, it's going to print the value of I each time. And it goes through. First time it's 1, second time it's 2, 3, and then 4. So we know it's working. I is changing the value throughout. Now all we have to do is like set it to something useful. So here we're going to want our output vector. And we're going to set the first value, or the ith value, as something. So we're going to go out at, and this is the subscript, which means a subset. So we're saying we want the output vector at whatever I is. So I is going to start at 1. So we want the first one's going to be out of at the first element, or the ith element, and we're going to set it to x plus y. Does this look right? So what do you think? If I went like this, and then would this be what I want? And then maybe I would write out at the end. So maybe someone who's more familiar with for loops can tell me. Would this work? Let's just try running it. I don't even know what's going to happen. Oh, sorry, I forgot to run. I have to run it all together. So I highlighted all, Command Enter, and it gives me 7777. So something's gone wrong here. Can anyone fix my code? I'm specifically going to say that there's something wrong in this middle part that I've forgotten in my for loop. Does anyone have any idea why it's running? So one way we can check this is we'll just set the value of I equal to 1. I'll just write it down here because I don't want to save this, but I'll set I equals 1. Now I is a value of 1. And now I can just run the middle of my code and see what's happening. So I'll just run the right-hand side. Okay, that's 7, 9, 11, 13. And then if I look at what out currently is, it's only supposed to be one thing. So out is only supposed to be, it's only one thing we're putting into it, but we're trying to put in on the right-hand side 4 things, but we only want one thing. So what the heck, what have I done wrong here? Does anyone know? The one thing that I'm missing is I just need to add this subscript. I'm just trying to, sorry, I'm introducing more problems because this isn't supposed to be about for loops, but if I just add these subscripts, what I really wanted it to do is I wanted to go through each of the values of X and Y and then add them together at each of the loops. So this is now giving me, at the first one, it's 7, and it'll save it into the first value of out. And just, so I guess what I was trying to say is that we're just missing, we were just missing subscripts there to get it to go an individual thing one at a time. So now if I try running this, we get 7, 9, 11, 13, which is what we wanted from above. So that's just the same thing. All right, so this is one way of doing it with for loops. This is a way easier way of doing it with vectorization. So we can see that like the vectorization way, this is the vectorization way, for loop way. And we can see that there's 2 different ways of doing it. For loops, we get kind of more control over exactly what we want it to do, but it's way more cumbersome to write. And it actually turns out that it's way slower as well. Whereas vectorization, super quick. And one way we can show just how quick it is using a package called microbenchmark. So if you haven't already, you'll have to just install this package. But it's a really good package, and since I've discovered it, I really love it actually. So I would recommend installing it. You just have to write install packages and then microbenchmarking quotations. Let me know if anyone can't get this to install. And then we're just gonna load it after it's loaded. But I'll just pause here because people are probably installing it. So don't worry too much about if you didn't understand the for loop part. If you really want yours to work, let me know. If anyone's really wants their for loop to work and it's not working, we can try and fix it together. But really what this is going to be about is more just showing you that the power of vectorization is way faster in general. Does anyone have any questions so far? I know I've been buzzing through this super quick. We'll do some actual like challenge questions in the next little bit. So this is kind of like mostly it, I think, for vectorization. Most of everything I can show you is pretty much done for vectorization. We'll just do a few challenge questions and then we'll move on to functions. This section is not very long at all. So I saw your good sign, cool. Has everyone been able to install microbenchmark as a package? Because it's fun to play around with. If you're looking for a challenge, I'd highly recommend trying it out. It's really fun to play around with because you get to test kind of what's going slow and what's going fast. And because I'm in like a lab where I'm running a lot of like what's called mechanistic models, there's like a lot of parts to it, and every single one of those parts slows it down. And it's kind of like the chemistry rule of like the slowest reaction is going to be the speed of the reaction basically. And it's kind of like that with coding. The slowest part of your code is going to dictate how fast your code goes. So if you can find the slowest part and identify it and maybe speed it up a little bit, it's going to make everything just churn way better and go way faster. So this is really the package to do that with, and I'll show you how it works in just a sec. Is everyone good with microbenchmark? Let me know if you're not, or you've got it down, you've got it installed. The way it works is really simple. We basically just make a list of what's called expressions. Oh, that's okay, Maxine, that's actually fine. It just means that The package is slightly more advanced than your system, but it should still work, hopefully. It's just a warning in case. But as long as it's just a warning and not an error, it should be okay so far. So then you just want to load it once you've installed it. And once you've installed it, you can also comment this off because you won't ever need this code again. Once you've installed it once, unless you update your RStudio, you should be good and you won't need to reinstall it again. It's kind of like buying a book and putting it on your bookshelf. And then when you've got the book on your bookshelf to load it, you just take it off your bookshelf with library. So library takes the book off the bookshelf, opens it up, you're ready to use that book. You're ready to use that package. So with microbenchmark, we can set like, I'm just gonna call it X1 to be really simple. X1, and this is how we just basically write what we're gonna evaluate. So if we've got two expressions or two things we're gonna run and test the time of, we're gonna write it like, we're just gonna name it something like X1 and X2. I don't really mind which one. We can even call it like for loop and vectorization. I think those names aren't taken, so it should be okay. And basically we just write for loop equals, and then in curly brackets, this is where we're gonna put whatever we're running. The code we're running, and we're gonna test how fast it is. It's gonna go inside these curly brackets. So for loop, I'm just gonna press enter, and I'm just gonna copy paste it. Copy this, and I'm gonna paste it here. Oh, that didn't work. There we go. So there's my for loop. Vectorization, exact same thing. Inside the curly brackets. Oh, and just remember the first curly bracket has to end with a comma. The second one won't have to because it's the last curly bracket, but because it's like a list of like expressions, you're gonna have a comma in between them. For vectorization, same thing, enter. And here we'll just copy what we have for vectorization. Oops, this one. Copy and paste. Oh, keep doing it in the wrong spot. There we go, paste. Okay, so it looks really weird and complicated, but basically all that's happening is we've got this part that's running a for loop within the curly brackets. And this part is running vectorization. Same exact operations. We're doing X plus Y, but they're both in curly brackets. And we can try running this. I think it won't be much different though, because we've only got 4 elements. So it's gonna be super close for time. So one thing we can do is we can change this to 100. So if we change the 4 to 100, and maybe we change X and Y to 100, and maybe Y is going to be 101 to 200, something like this. This is going to make it slow down a lot. So this will make it now really slow. So all I did was I just changed it to a different number, to a higher number rather than 4. So now X and Y contain 100 elements each. So 100 elements each, when you're adding them up, we're going to see a difference in speed now. So if we try running this, command enter, what microbenchmark will run is it's going to go through the operations and it's going to run them 100 times each. So by default, it runs them 100 times each. And then it counts the nanoseconds in this case, but it sometimes is a matter of seconds or even minutes. And it will compare them in this nice table for you. So for instance, in the for loop case, this is the for loop, what we were running in the for loop. The minimum amount of time was this many nanoseconds, which is a lot more seconds than clearly vectorization. So you can see a huge performance difference in terms of the for loop versus vectorization. So right away we can see, and I usually look at the mean. So because it ran it 100 times, sometimes your system is slow for different reasons. For instance, I'm streaming on Zoom right now, probably doesn't help the speed of it at all. But because it's running 100 times with replication, we can really compare the means, and we can see clearly for loop way slower in terms of nanoseconds than the vectorization. I can't tell you how many nanoseconds adds up to a second, but we can see that if we had more and more complicated operations using for loops, it's going to be really slow on our computer. So that's why I love this microbenchmark thing. It really is a nice way of seeing all the data. Once I figured this out, finally, I started using it excessively. So I highly recommend. Microbenchmark is awesome for that. Sorry, that was a bit of a random tangent. Does anyone have any questions about microbenchmark or anything like that? There's some options you can also set as well. If you search in the help page for microbenchmark. For instance, you can set the number of times it runs. It currently is a default of 100. So you can set it to like 5 if it runs really slow, if you have something that runs really slow. Does anyone find this, is anyone going to use this, or is this like completely too far in advance right now? You like it? Cool. Awesome. Okay, so now we're going to move on to a couple of challenge questions. To do these challenge questions, we're going to need to reload that gapminder data set that Jacob was plotting in the last workshop. To get that, we can use we can load the gapminder data set. So if you have it loaded, if you don't have it installed though, you're gonna have to go install packages gapminder in quotations. So you have to install it if you haven't already, but otherwise you can just load it with library gapminder. And I think now if we look at the data set by going head of gapminder, yeah, so we've got it there. So it should load the data set pretty well. This is so much easier now that we've got this library gapminder. Then we used to have to like, we used to have like a text page that you had to like load. It was this, and we had to direct you guys to this website, save it as a page, and then like find in your working directory. It was like super complicated, but now we just do it this way, which is way easier. So can everyone get the gapminder data set to print using library gapminder and then head? If you see it here, that's good in your console. I'll just pause to make sure that everyone can do that. Cool, we got one yes. I can't see everyone, I'm just gonna make my screen bigger. Cool, 2 yeses, awesome. Yes and yes, good, good. Okay, cool. I think yeah, that's everyone, I think. Everyone who's doing it. I'm not sure Natalia's doing it with us, but all right. So here's a challenge question using this data set. So knowing what you know now about vectorization and for loops, you can make a for loop if you really want. It'll be really slow, but you can try doing this with the for loop. But here's the challenge. Using the population column of the gapminder data set, make a new column in the same gapminder data frame that contains the population in units of millions of people. So we're going to transform in the gapminder data set. We get this population thing, and it's nice and all, but it's a really big number. And when you plot a really big number, it takes up a lot of space in your graph. It's not super good. So it's actually better to just try and plot this population column as millions, in units of millions. So we can actually just, as you can imagine, there's some kind of operation we could do that will transform it into units of millions of people. Can anyone guess what we would do to this column? In terms of, you don't have to say the whole code, just say like, what would we do if we want to get in units of millions of people? What would you have to do to the column? Any guess is fine, even if it's, would be multiplying or dividing by to get it in units of millions of people? Any ideas? Remember, this is a big number. So what we're going to do to get in units of millions of people? No one's feeling brave today. Well, 2 ways to go about this. We could do this, and if we times it by millions of people, let's see what that goes to. So a million is 1e⁶, or what 1e⁶ is just scientific notation in R for a really big number. It's 1 followed by 6 zeros. So 1, 2, 3, 4, 5, 6 gives us 1e⁶, or 1e⁶. This is a million basically. It's just represented in a different way. We can also write it as 1, 1, 2, 3, 4, 5, 6. This is the same as a million. So either way, this produces 1e⁶, or you can just write it 1e⁶. It means the same thing in R. So this is a million. Let's say we did this is not the way I would intend it. So if we thought that it was units of millions of people and we times it by it, we actually get like a crazy big number then. So that doesn't seem right. If we want it in units of millions of people, what we actually want to do is divide it by, right? So if this is the number of people and we want it in units of per like millions of people, if we divide it by a million, we get, this is about 8 million people. So 8.42 millions of people. So that's kind of what we want to do. But this is just the first value of the column. So if you look at the gapminder data set, this is just the first column of it. So how do we do this to the whole column? Let's say we want to do maybe some kind of vectorized elements thing. What would you do? And this is a challenge for you guys. So this is a challenge for you guys to do. How would you get a new column of people, which is a unit in units of millions of people? Remember that when you're working with data frames, if you're referring to a column that exists or a new column, we have to write the data set name first, gapminder, and then a column we're referring to, or it can even be a new column that doesn't exist yet. We can define it with a $sign and then something written after this. So for instance, for the population, we go gapminder $pop. This gives us just the column population. And yes, you can also use mutate. Good point. We're not quite there yet. We haven't introduced it in this course yet, but mutate is actually a very good option. And that's what I would normally do. Mutate from tidyverse. We will get there. We're just not there quite yet. I think it's the next. It's in like 1 or 2 sessions from now. We're going to talk about dplyr and using mutate and summarize and things like that. Those are super useful. But right now we're just trying to do it with using basic R. How would we do? How would we make this in millions of populations? So I'll just pause here. If you can let me know when you've got it. And if you feel comfortable sharing your answer in the chat, feel free. But how would we answer this question using a population column of the gapminder dataset, make a new column in the same dataset that contains the population in units of millions of people? How are we going to do this? Anybody got a answer so far? I might have missed it if the cool. How would you do it, Lauriane? Brilliant. Yeah. Exactly, Ryley. That's perfect. Yeah, so the real key here is knowing that you can define a new column just from this $sign. We can just go like population in millions, or we can do it the way you've done it. This is called camel case because we've got like letters that are that are capitalized, but we can do it in camel case as well. And basically we're taking an existing column that already exists, gapminder $pop, and all we have to do is divide it by the number in millions, and we get a new column, popMil. And we can look at this column if we just highlight it and run it. We can now see it's in much more readable units, way easier for plotting. And now we can try plotting it actually. So let's try plotting. What does it want us to do? Plot the population millions against years. So let's try plotting it with ggplot2, if anyone remembers this. Plot popMil by the year for all countries. So we can try doing this. We're going to need ggplot2. And who was here in the past 2 sessions? There was one just before we ended for the year for the year that Jacob did, and one last week that Jacob did. Does anyone remember how would we plot this in ggplot2? And this is a little bit tricky. ggplot2, it takes some practice, so don't worry if you can't remember. So if we're using ggplot2 to plot, you can see here it has a few things we need. We need the data argument, so that's whatever data set we're using. And then we need some kind of aesthetic, which is AES, and that defines what's going to be like the variables we're plotting. And then after this, we're going to add some geomes. So if we want, for instance, points, we're going to add geome point. Oops, that's not the point. So that's kind of how it's going to start. So data, what is the data? The data is the gapminder data set. Now we're going to define some aesthetics where we've got X and Y. We need at least X and Y. We can't do it without an X and a Y. So if we're making like a scatter plot, for instance, what's going to be our X and what's going to be our Y? Can anyone write in chat? X is going to be something, Y is going to be something. So just as a refresher, well, maybe someone's answering. Aesthetics is just kind of where all your variables, this is where we're actually choosing a column of the data set and we're going to use it. So for instance, in gapminder, currently what we have for the names, this is the column names. We've got country, continent, year, life expectancy, population, GDP per capita, and population mil, which is one that we've created. And thank you, Lauriane. Year we're going to have as our X, year, and our Y is going to be pop. Now, let's try running this. Oh, but one thing's going off here. Object year. And I think this is maybe because it's autocorrect, not actually what you meant to write, but object year not found. So when this happens, this is a quintessential error that you'll run into many times. It's because of it's our own faults. I did something a bit silly here. It's case sensitive, right? Thank you. Perfect. So yeah, so year was actually lowercase. If we look at the names in the original data set, year was lowercase. So just by changing that, hopefully this works now. Try running that. And then my plotting window is kind of small and I pray it doesn't crash my R. My computer is really terrible, so sometimes it crashes. So there we go, we got population sizes across time. There's so many different countries, so it's kind of hard to tell which one's which. We can also add like colors, so color equals, and then we can just do another thing like maybe continent might be okay. Let's see if this does. Okay, so what it's going to do is going to group by continent now. And so there should only be, or actually no, it might do it individually. Yeah, so it's doing it by each different country. So, but anyway, we're producing a plot. That's the main thing. I think if we group by country or continent, this is, I'll never stop if I go down this rabbit hole, but anyway, you get this idea. We can add a line to it, geome line, try running it all. See if that does anything different. Probably just gonna look like spaghetti. Oh, that wasn't what I wanted. Anyway, you get the idea. We're getting a plot. And we'll go more into ggplot stuff a little bit later into when we go into dplyr, but most of it was covered in the previous session. So I'm gonna avoid going down the plot rabbit hole. All right, so that was a plot using our, oh, and sorry, one thing I forgot though, is we wanted the population mil instead. So we can actually use popMil, because right now you can see the axis label is a little bit hard to read. So if we use our custom column we created, popMil, we'll actually see it's much more readable now, as you can see. So if we've got a population in millions, 0, 500 million, 1,000 million, there's a bunch of Asian countries that have, you know, well over 100 or 1,000 million people, which I guess is 1 billion people within them. It's probably China on top, I imagine. I'm not sure, but large population sizes. I'm guessing probably China. All right, and India as well up there. Okay, so that was plotting with ggplot2. And one last thing before we end. There's a thing here about matrix multiplication, but if anyone is interested, I can cover matrix multiplication. But otherwise I was going to skip it because we don't do matrix multiplication a lot. But if you want to do matrix multiplication, the symbol is you just write percent times percent is matrix multiplication. So if you don't know what matrix multiplication is, don't worry about it. It's not super useful. It's just a way, if you combine vectors, matrices together, sometimes you have to do this. It's really good for like summing up, multiplying and summing things up really quickly. So that's what it's used for, but don't worry about it otherwise. I think I'm getting a package. All right, and one last thing, there we go. So one last thing we can do is we can actually do the same thing, but with logicals. So we can vectorize logicals. So let's say we want whenever x is greater than 50, we can make this trues and falses. So remember, x is a vector from 1 to 100. And when it's over 50, we can just write something like this, where when x is greater than 50, return true. So here it's saying the first 49 results false, and then as soon as it's over 50, it's true. So and if we wanted greater than or equal to, we could do it like that. And we can even save this into something called a, and then look at it from there. But anyway, that's just using logicals. So this all works as well with logicals, logical expressions. I'm not sure how useful that is to everyone, but anyway. All right, so that's it for vectorization. Let's just move on now, and we can start on functions if everyone's okay with that. Does anyone have any questions before I move on? That might have been a little bit dry at the end, but functions are really, I think, really useful. And when you get more into R, we build a lot of them. And honestly, I know so many PhD students who couldn't, like they use R a lot, but they won't be able to write their own functions. So I think functions are really overlooked. So I'm happy to jump into that if everyone's okay with that. Functions. Yes. Okay. I have a recipe for functions, and it's a lot like my for loop recipe. It's really, because I have to teach functions in the first class of R of the semester to my SC 2202 students. I don't know why it's written that way, but I have to teach them a function for their first assignment, which is just awful because nobody gets functions. But basically, functions, we got to assign them a name. The first thing we got to do is we got to name them. So like, I guess if I had to make a stepwise list of this, step 1, name your functions, your function. Something that makes sense usually. So if it's doing something that, you know, you want it to do, let's say, we're going to build a function in just a sec that will make more sense, but this is just an example. This is just going to be like code that doesn't work, but I'll show you what it does. So step 1, name your function, and we're assigning it a value. This is where we're assigning it the value of function. So function is the function that creates functions. It's a bit ironic, but you just write function and it's going to create functions. Step 2, write your parentheses in place. So there's 2 parentheses you're going to use. Your conditional, or sorry, this is actually your arguments, function arguments, and whatever the function is doing. So I always start this as parentheses like this and curly brackets like this. Always, always, always just write these out, I think, in advance. It's really helpful just to write them out, because if you don't, you might forget a parenthesis somewhere and then you get really confused what's going on. So the first little parenthesis, this is what we call function arguments. So whenever you write a function, you're going to have arguments. For instance, the microbenchmark has a bunch of arguments. It's got a list argument. It's got the number of times you're running it. It's got these ... dots, which means you can add as many arguments as you want to it, but I wouldn't use that just yet because it's a bit advanced. But basically, we've got all these arguments, and it tells us, it's kind of like different options that our function will have. Or it's also the input. So whatever you're inputting has to go in this part here. It's what we're expecting the function to receive. So for instance, if we're receiving like, this is like argument 1 equals something. It doesn't have to have an equal, but we'll have argument 1, argument 2. We could have many more. We could have 5. It's up to you, but it's going to be whatever's going inside your function. And again, usually we want to name it properly. So we want to name it whatever your function is doing. We'll name the arguments accordingly. For instance, if we want it to run a certain number of times, we might write it as like n times equals 100. And if you write equals 100, that means that the default value is 100. But you don't have to set a default value either. We can just write it like this. And that means that we're not setting a default value. We kind of expect that to automatically be input, but we don't have to have a default value. So we can maybe add step 3, write defaults for any function arguments. So the defaults, again, if we want like the number of times equals 100, just as we have here, the default is 100L. That's our number of times we expect an input. That's like our default for the number of times, but it depends on what your function is doing. So for now, I'm just going to write in, I'll just write this like example number of times equals 100. But for now, I'm just going to change this back to I'm actually just going to write this with just one argument, or maybe just arguments or something. I don't know. This code is not going to run properly. I'm going to show you an actual function in just a sec, but this is kind of like your skeleton code that you use. So now the next thing I do is in these curly brackets, this is where we want the function to do a bunch of stuff. And here's where I always just tell students just to click in the middle, press enter, and maybe add a little bit of extra space. Just press enter a bunch of times. Space doesn't matter in R. Space is automatically, it gets rid of it anyway, so you can add as much space as you want. For instance, I added space between here and here, here and here, here and here. I like spacing. It makes it look nice. So add space frivolously, it doesn't matter. And here's where we want it to do something with those arguments. So here's where we're like taking those arguments and we're performing an action. So it might be like, example, arguments. We're taking that arguments, which might be a vector plus 3 or something like that. So we want to add 3 to every single element of that vector maybe. I'm not going to write something actually in here, but then, well, we could do this, I guess. We could go like arguments plus 3. And then finally, we're going to, at the very end, this is always what we do right before we end our code. We have to make it return a value / object. But more like it's actually return an object as output. So this is where we might go, and we can actually use a command for this. We can use the return command, return, and we want it just to return arguments, maybe plus 3. So what we might want to do actually is maybe want to save this as an out vector. Remember our out vector from before? So if we save arguments plus 3 as an out vector, now we can return, instead of arguments plus 3, we just return out. So this is this is like the bare bones of a function. And this is, when we're doing this, we're just defining a function. We haven't actually used it yet. So it won't actually do anything until we actually use it. But what this function is going to do is it means we can do really complicated stuff. For this step, instead of just one step, we can have like everything we need it to do all in this function. And then we only have to run the evaluation of the function once. And now we've got our own function. We can apply it to any case that we need. So the more and more you build functions, the more you get good at kind of dealing with things within the function. So I can try running this. And this actually should work okay, I think. So now if we want to use my function, we write my function. And we're going to use it on, I don't know, a value of 5. So what it should do, 5 is going in as the arguments. Arguments goes here. Arguments is a value of 5. So it's 5 plus 3 when it goes to this part. 5 plus 3 is 8. Save it into the out object. And then finally, it's going to return out. And it's just going to return out. It's not going to return anything else unless we tell it to. So it has to be within this return object. So if I try running this, it should be 5 plus 3 equals 8. There we go. So that's, if you can get that to work, that's basically the hard parts are done. If we can just get something basic to work. So if you want, I can copy this in case it doesn't work and put it in the chat. Just note that it might not copy super perfectly sometimes. It doesn't copy because it adds like extra symbols from the Zoom chat. So just watch out. If it's giving you any X's on the side of your screen, that means something bad has happened to the copied code. So just watch out for that. Yes, and it will also work on a vector because of the way I've built it. So sometimes it won't. It really depends on how you've built it. But here you can see, if you imagine that arguments was a vector, and now we've got a vector of like 1, 2, 3, 4, 1, 2, 3, 4 plus 3. Will that work? Well, yes, because R is good at vectorized operations. So we'll do 1, 2, 3, 4, each of them element-wise plus 3, and it'll save it as out. Out will now be a vector instead of one number. And when we return out, it will be the number of output will be the same as our input, basically. So if we try my function, let's make a vector first. Well, we got this X vector, right? So our X is from 1 to 100. If we go my function on X, all it's done is it's taken each number and it's added 3 to it. So plus 3, plus 3, plus 3, plus 3, plus 3. So even though this is really simple, and obviously we do it a better way, this is the building blocks for like really complicated operations when you do this in your own code. So you might have like a really complicated thing you're doing. I've even built them so it goes and it actually loads in the data set, pre-process a certain data set, spits it out, and then I've got all these data sets processed and I can quickly glue them together in the right format. And then you've got your like big data set of everything. So it's really good at that. Like once you get into it, you can really start getting really complicated. It's just, you need to get the middle part working first properly. So let's try an example of making something that is actually kind of useful, I think. I'm always confused with Fahrenheit to Celsius calculations. Fahrenheit to Celsius confuses the heck out of me. I'm Canadian, so we use Celsius, just like Australians. But whenever Americans say Fahrenheit, it confuses the heck out of me. Let's make a function that calculates degrees Fahrenheit and converts it to degrees Celsius. It won't have any units there. We're going to ignore degree units. It's just going to be the numbers, but let's try and do this. So we're going to make a function that converts Fahrenheit to Celsius. I forget how to spell Celsius. There, I think it's like that. So degrees Fahrenheit to degrees Celsius. All right. So what's one example? What can we name our function? First step. What are we going to name our function? Give me something that makes sense. Don't give me like nonsense, but. Fahrenheit, okay, let's use it. Fahrenheit to 0C, which is degrees Celsius. Okay, sounds good to me. So we got this function and it's case sensitive. So we've got that O, which is lowercase. So just remember that when we're writing the function after. And we're gonna write, the next step is we just write function. And then before we forget anything else, let's write our parentheses in, because that's always really important. So that's kind of step 2. Step 3 is if we have some kind of defaults, we can put that in as the argument. But otherwise, let's just maybe put in an argument name. So what's our argument name going to be for this input? So if we're inputting Fahrenheit, what would we call maybe the input value that we want, or vector even? We want it to be here. So before we use arguments, but that was like a naive kind of example. Here we want to maybe be more specific. What are we going to name this? Like our input vector. I like convert Celsius to Fahrenheit as well. So we got like the very short name for the function, the very long name for the function. I like that. Okay. I would probably go for something in the middle. Yeah, I like Fahrenheit value. I might just do it lowercase just because I like lowercase, but we can go Fahrenheit value. And then we can even set a default if we want. So I don't really know a good default, maybe 0. I don't really know what degrees Fahrenheit 0 is. So I'll just set this as the default value as an example, but we don't have to set a default. It can just be like this, but I'll set it as a default of 0. Maybe we'll make the default 0 degrees Fahrenheit. So that's what we've done here. So that's kind of step 3. And I didn't finish my steps, but basically step 4 is just draw the owl. It's the hard part. Step 4 is use the arguments to do what you want. And step 5 is save what you did as an object and return it at the end of the function, which is a step that I think everyone forgets. Is if you do stuff and you don't return it, nothing will happen. It'll just run everything you wanted it to, but it won't give you anything out. So you really need this return step at the end. And you don't have to have this return. You can just write out. But I find it easier if you just write return, because then it forces you to remember, yeah, we're returning it. And actually, if we try returning, it will actually not work outside of a function. It'll only work inside of a function. So it's actually, it's designed specifically just to be used with function. So we won't actually be able to see it unless we highlight just out and run what out is. But anyway, all right. So we got the default set. We're good to go. And thank you for the conversion. Actually, that's awesome. I have it here as well, but that's super helpful. So the conversion is just as Ryley puts it. We want Celsius as Fahrenheit value. I'm actually just going to copy what you wrote. This is perfect. So we do the manipulation. So we're doing the conversion here to Celsius. I think it's in the S, I think. I'm just going to make it lowercase. Maybe I'll write Celsius value just to be consistent. And as you wrote it up here, we want it to be the same as up here. So I'm just going to write this as Fahrenheit underscore value. Yeah, perfect. So now what we're doing is with 0, we're going to subtract 32 off of it. Then we're multiplying by 5/9. What the? How do Americans come up with this stuff? Like, how did this? I don't understand this. I need to look up the history of Fahrenheit. It just makes no sense. And they say, anyway. And so if I run this, and I have notice I'm missing one step here. Hey, yeah, you're here. The Americans here. Notice I'm missing one step here. Just note to yourself, I'm missing a single step. What am I missing? And I'll just show you what happens if I'm missing it. So I'm going to go Command Enter. This If it doesn't give me any error messages, that's good. That means it's defined the function, but then we just need to use it. And yes, you're absolutely correct, Ryley. So FToC. Now we're going to use our function. So we're actually going to employ it. It even gives us, since we've defined it now, it gives us the argument. The default argument is 0. So here we're going to write Fahrenheit value maybe equals something else. Right, value equals 10 degrees. Let's go 10 degrees and see what this does. And we run it and nothing happens. This is where you should be concerned. If you're running your function, not defining it. So here we're defining the function. We're just telling what's our definition of this function. Here we're actually running it. If we run this function and nothing's happening, we missed something. And Ryley's exactly right. We've forgotten the last step, which is we have to return it at the end of the function. All right, so we got to return the Celcius value. We saved it in the function, but we never told R to give us back the Celcius value. So finally, because R is kind of annoying, we have to return the Celcius value. And here we just go return Celcius value. And finally now if I write this and I try rerunning it, it still doesn't work. And why is that? It's just because I forgot to redefine it. So I've got to go back up here, redefine my function, highlight it all. So don't forget, you got to highlight the whole function because it's got these brackets around it and it won't work unless you highlight the whole thing. Command enter, it's redefined it. And now finally we can try reusing it. And we see that 10 degrees Fahrenheit is negative 12 degrees Celsius. And my favorite temperature, does anyone know the temperature at which the two are equal, Celsius and Fahrenheit? Where the two are equal? Yeah, minus 40. Us Canadian Americans know it because it's the only point where we can agree on. It's very cold then. Minus 40 Fahrenheit is minus 40 degrees Celsius. And Legana has a point as well. If you can use Markdown as well. We haven't covered Markdown yet, but it will be super useful as well to define your function in a kind of like a separate part of your document and then use it elsewhere. But here we're just kind of doing all those steps together. So it's kind of just like a basic thing right now. Notice that we can also don't need this Fahrenheit value. Since our first argument is Fahrenheit value, we don't actually need that. We can just run it without and it will still run. But one thing we can do to make it cause an error is we can add in characters. Like if we did like 40 degrees Fahrenheit, error, non-numeric argument. So it doesn't like this 40 degrees Fahrenheit. So that's one thing that we can improve on this, is that sometimes the user, maybe it's not us that's using this function. Maybe we built this function for someone else and they tried to input it as a character string. And this, I would argue that this kind of error message isn't super helpful. So there's another thing you can do is you can actually test to see if something is the correct format you want it, and then produce your own error message if it's wrong. So we can even put in something like test to see if Fahrenheit value is a numeric. Here we would do something like if statements. Does anyone ever remember conditional if statements? So we can write if is numeric Fahrenheit value. This is asking, is Fahrenheit value a numeric variable? And if it is, if this is true, what do we want it to do? We want it to stop. And we want it to say the error message, Fahrenheit value must be input as a numeric vector. So we can write our own error message like this. We could do something like this, or we can be like, we can write whatever we want, like good luck, Jacob, tomorrow or something. We can run this now, reevaluate it. What do you mean? And then I'm confused. Oh, and then I guess it's not working. Oh, weird.
It's because you're testing if it's numeric and the input should be numeric. So it should be if it's not equal to numeric.
Gotcha. Yeah, thank you. Yeah, I see it now. So one thing about logicals is, and here's what I could do. This is a good point. Last thing I'll do is just how to debug this. So let's say it's not doing what I want. I really want to work exactly where it's breaking down, because Legana just has eagle eyes and saw it way before I realized. But let's say I didn't have any clue where this broke. So the last thing I'll just show you is how do we debug a function if it's not working. The first thing I do is I always just define whatever arguments there are. So if we look at Fahrenheit value, what's inside of it right now, it doesn't exist. So the first thing I'll do is I'll just make sure that each of my arguments is evaluated as it is. So I'll set it to the default value in this case. I'll write Fahrenheit value equals 0. I might input the data set into whatever the argument is for the data set if I was inputting a data set to it. And I'll just run it. So now I've got a value for Fahrenheit value. It's a value of 0. So I've got some value going in. Maybe actually I'll do it with the thing that doesn't work. So right now I'm trying to set it to something that doesn't work. So I'll set it Fahrenheit value equals to 40 degrees Fahrenheit. That's the thing that shouldn't work properly because it's a character string. So the next thing I'll do is I'll go down each of my steps and see where it breaks. So for this next one, if I try running this actually runs okay. There's no error message there. But this is the part where it should run an error message, right? I set it to a value that shouldn't work. I set Fahrenheit value to 40 degrees Fahrenheit as a character string. It shouldn't work because it's a character string. We can't, down here, if we try running it, this is where we get our error message. So it's still not working. This is where we should have caught the error. So now I know, oh, wait a second. Given my big brain, I realized that the error is right here and it should have stopped here. For some reason, it didn't. So now I'll try and just run this one line piece by piece to see where it's breaking. So the first thing I'll do is I'll look at, okay, is Fahrenheit value right? Yeah, that's what I define it as. Going out from that, the next parenthesis, is this right? Is numeric Fahrenheit? And it says, no, it's not a numeric. Okay, so that's good. But now I realize the next thing out is the if loop. And if this is a numeric, it should be, this is true actually. So I need this to be, instead of returning a false, I need this to be return a true. And the way you invert that with logicals is you just add an exclamation mark. So for instance, if I write exclamation mark on, I don't know if this is gonna work actually, true, it returns false. And if I write, I don't know if this will work. If you write double, apparently it does. If you write double exclamation mark, it's going true, false, true. So it always inverts it based on your exclamation mark. So now when I run this is returning true finally. So this is actually asking, is it not a numeric? And that's what I was going wrong. I was asking the wrong thing before. So if it's not a numeric, it now says, yes, this is not a numeric. And finally now, if I run this, it's gonna say stop. And it says, good luck, Jacob. So finally it's returning the right error message and it's stopping before I get to the part that is actually important. So this is a way of kind of making your function run properly now. So does everyone, I'll cover this again maybe next week if I do a little bit more in functions, but does everyone kind of get the gist of what I'm talking about? Don't worry too much if you can't build your own function yet. We'll do it again next week. But now hopefully this works. There we go. Now it's giving me the error message I wanted it to do. Good luck, Jacob. So it's got, you can customize your own error messages. Clearly it's not going to work when I put in a character string, but now if I put in like 100 degrees Fahrenheit, what I really need it for actually is baking. I always get confused by baking. What is it, like 200 degrees Fahrenheit? Or no, 400? It's the one they always use. Confuses the heck out of me. Yeah, good point. I like the chat. All right, so that was building our own little function here. Does everyone kind of get just the bare bones of it? I think I'm out of time now. But that's kind of how you go about writing a function. The first thing you want to do is just kind of build the middle of it, make it return a value. If you can make it run a really simple like outputs, then you can start building more complex features into it, such as this, where we got it right, returning our own error message based on the inputs. So if we put in the wrong input, we can make it return an error message. Awesome. I'm glad it was easy to follow. But don't worry if you don't get it. Functions, again, as I say, most PhD students I know, if I went up to them and asked, write me a function to convert Fahrenheit to Celsius, they would be like, no, I'm not doing that. So don't worry if you don't get it. It actually is pretty hard to like grasp functions at first. But I think the easiest way is just follow my recipe.